The 40 degrees Celsius terminal rating on the Federal Pacific breaker means it is approved for use with conductors having a temperature rating of 40 degrees Celsius. This temperature rating is a common rating for conductors used in residential and commercial buildings. Back in the 1940s, when this breaker was likely installed, the conductor sizing standards were different than the standards of today. For example, it was once common to use 12 American wire gauge conductors on 30 amp circuits. However, the National Electrical Code today requires using 10 American wire gauge conductors on 30 amp circuits. If you were installing one of these Federal Pacific breakers in modern times, it would be necessary to use conductors rated for 40 degrees Celsius and size following the specifications in the National Electrical Code. For a 30 amp circuit, this means using 10 American wire gauge conductors. No code requirements exist to prevent anyone from installing a Federal Pacific breaker now. However, these breakers are no longer manufactured and have a history of causing electrical fires. Therefore, it is generally recommended to replace Federal Pacific breakers with new breakers made by a reputable manufacturer. When determining the correct conductor size, several factors come into play, with the ampacity of the conductor being a primary consideration. Ampacity refers to the current, in amps, that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. The National Electrical Code provides tables, such as Table 310.15, the 16, that list the ampacities of various conductors based on their size, insulation type, and insulation conditions. To use these tables effectively, one must first identify the applicable temperature rating of the terminals, in this case 40 degrees Celsius, and the insulation type of the conductor being considered. The National Electrical Code requires that the conductor ampacity be selected based on the lowest temperature rating of any connected termination, conductor, or device. This means that if the breaker terminal is rated for 40 degrees Celsius, the conductor's ampacity must be determined using the 40 degrees Celsius column in the ampacity table, if one exists for the specific insulation type. However, as mentioned, 40 degrees Celsius columns are not explicitly present in the commonly used National Electrical Code ampacity tables like 310.15, the 16. In situations where the terminal temperature rating is lower than the conductor's insulation temperature rating, it is necessary to use the ampacity corresponding to the terminal's lower temperature rating. If the table doesn't list a 40 degrees Celsius column, you would typically refer to the 60 degrees Celsius column for conductors rated 60 degrees Celsius or higher, or even the 75 degrees Celsius column if the conductor is rated 75 degrees Celsius or higher and all terminations are rated accordingly. However, when dealing with the 40 degrees Celsius terminal rating, a more conservative approach is warranted. Since you cannot directly find the ampacity for 40 degrees Celsius, you must ensure that the conductor chosen can handle the load current without exceeding the breaker's terminal temperature rating. This often involves selecting a larger conductor size than might be required based solely on the standard ampacity tables. To determine the appropriate conductor size, you must consider the specific application and installation conditions. Firstly, calculate the load current. This is the actual current that the circuit will be carrying. Secondly, refer to the National Electrical Code Table 310.15, the 16, or the appropriate table for your specific situation, and find the ampacity of different conductor sizes at both 60 degrees Celsius and 75 degrees Celsius. Thirdly, compare the calculated load current with the ampacities listed in the table. Select a conductor size that has an ampacity equal to or greater than the load current, but also consider the 40 degrees Celsius terminal rating. If the load current is close to the ampacity of a particular conductor size at 60 degrees Celsius, it might be prudent to select the next largest size to ensure that the terminal temperature rating is not exceeded. In some cases, it may be necessary to perform calculations or consult with a qualified electrical engineer to determine the appropriate conductor size. These calculations may involve directing the conductor ampacity based on factors such as ambient temperature, the number of conductors in a raceway, and other installation conditions. Derating reduces the allowable ampacity of a conductor to account for the effects of heat buildup and other factors that can reduce its ability to dissipate heat. For example, if the ambient temperature is higher than the temperature listed in the ampacity table, the conductor's ampacity must be derated to account for the increased heat. Similarly, if multiple conductors are installed in a raceway, their ampacity must be derated to account for the mutual heating effect. The National Electrical Code provides detailed guidelines for derating conductor ampacities based on various factors. These guidelines can be found in Article 310. It is important to carefully review and apply these guidelines to ensure that the conductors are properly sized for the specific installation conditions. In addition to ampacity, other factors must also be considered when selecting conductor sizes. These factors include voltage drop, insulation type, and environmental conditions. Voltage drop refers to the decrease in voltage that occurs along the length of a conductor due to its resistance. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The National Electrical Code recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To minimize voltage drop, it may be necessary to select a larger conductor size than would be required based solely on ampacity considerations. The insulation type of a conductor also affects its suitability for different applications. Some common insulation types include THHN, THWN, and XHHW. Each insulation type has its own temperature rating, moisture resistance, and other properties. The insulation type must be selected based on the environmental conditions and the type of equipment being served. For example, conductors installed in wet locations must have a moisture-resistant insulation. Environmental conditions can also affect the selection of conductor sizes. Conductors installed in corrosive environments, such as near saltwater or industrial chemicals, must be made of materials that are resistant to corrosion. Similarly, conductors installed in direct sunlight must be rated for sunlight resistance. When installing electrical equipment, it is important to follow all applicable codes and standards. The National Electrical Code is the most widely adopted electrical code in the United States. It provides detailed requirements for the safe installation of electrical systems. It is important to consult the latest edition of the National Electrical Code and any local codes or regulations before beginning any electrical work. In addition to the National Electrical Code, other standards may also apply. For example, Underwriters Laboratory standards provide requirements for the safety of electrical products. It is important to use only listed or labeled equipment that has been tested and certified by a recognized testing laboratory. When working with electricity, it is important to take all necessary safety precautions. Always energize circuits before working on them. Use appropriate personal protective equipment, such as gloves and safety glasses. If you are not qualified to perform electrical work, hire a licensed electrician. Working with electricity can be dangerous, and it is important to take all necessary precautions to protect yourself and others. Federal Pacific Electric, or FP, breakers have a known history of issues. Federal Pacific Electric, once a prominent manufacturer of electrical circuit breakers, is now widely recognized for producing breakers with a significant defect. This defect, which can prevent the breakers from tripping in overload or short-circuit conditions, poses a serious fire hazard. The issues surrounding FB breakers have been extensively documented through independent testing, legal proceedings, and reports from electrical safety experts. These findings have raised significant concerns about the safety of homes and buildings equipped with these breakers. The primary concern with FP breakers is their high failure rate. Under normal circumstances, a circuit breaker is designed to trip or switch off when the electrical current in the circuit exceeds a safe level. This tripping action is intended to protect the wiring in connected devices from overheating, which can lead to fires. However, FP breakers have been found to fail to trip in a substantial percentage of cases, leaving circuits vulnerable to dangerous overcurrent conditions. Independent testing has revealed that some FP breakers fail to trip as often as 1 in 4 times. This failure rate is significantly higher than that of other breaker manufacturers and poses an unacceptable risk to homeowners and building occupants. The reasons behind the FPE breaker defect are complex and relate to the design and manufacturing processes used by the company. One key factor is the use of substandard materials in the breaker's internal components. These materials can degrade over time, leading to loss of functionality and an increased risk of failure. Another factor is the design of the breaker's tripping mechanism, which has been found to be prone to sticking or jamming. This can prevent the breaker from tripping even when the current exceeds its rated capacity. The issues with FPE breakers first came to light in the 1980s when the Consumer Product Safety Commission, or CPSC, began investigating reports of breaker failures and electrical fires. However, the CPSC never issued a formal recall of FPE breakers despite the evidence of their defect. This decision has been widely criticized by consumer advocates and electrical safety experts. Over the years, numerous lawsuits have been filed against FPE and its parent company, Reliance Electric, alleging that the company knowingly sold defective breakers that posed a fire hazard. Some of these lawsuits have resulted in significant settlements for homeowners who suffered damages as a result of FPE breaker failures. Today, FPE breakers are no longer manufactured, but they can still be found in millions of homes and buildings across the United States. Many of these breakers are decades old and may be even more likely to fail due to age and wear. If you have FPE breakers in your home or building, it is important to take steps to mitigate the risk of fire. The first step is to have a qualified electrician inspect your electrical panel and identify any FPE breakers. The electrician can then test the breakers to determine if they are functioning properly. If any breakers are found to be defective, they should be replaced immediately with new breakers from a reputable manufacturer. It is generally recommended to replace all FPE breakers in the electrical panel, even if some of them appear to be functioning properly. This is because the risk of failure increases over time, and it is difficult to predict which breakers may fail in the future. When replacing FPE breakers, it is important to choose breakers that are compatible with your electrical panel and that meet all applicable safety standards. The electrician can help you select the appropriate breakers and ensure that they are installed correctly. In addition to replacing FPE breakers, there are other steps you can take to improve the safety of your electrical system. These steps include ensuring that all wiring is in good condition, that all outlets and switches are properly grounded, and that ground fault circuit interrupters are installed in areas where water is present, such as bathrooms and kitchens. It is also important to avoid overloading circuits by plugging too many devices into a single outlet or extension cord. Overloading circuits can cause the wiring to overheat and potentially lead to a fire. Regular electrical inspections are also recommended to identify any potential problems before they become serious hazards. A qualified electrician can inspect your electrical system and provide recommendations for improvements or repairs. By taking these steps, you can significantly reduce the risk of electrical fires and protect your home and family. The presence of Federal Pacific Electric breakers in an electrical system raises significant safety concerns due to their documented history of failure. Here's a breakdown of why they are problematic and what steps should be taken if they are found. The primary issue with Federal Pacific Electric, or FPE, breakers is their tendency to fail to trip during an overcurrent or short circuit event. A circuit breaker's fundamental function is to interrupt the flow of electricity when the current exceeds a safe level, thereby preventing overheating and potential fires. Studies and testing have shown that FPE breakers have a significantly higher failure rate compared to modern breakers, meaning they may not trip when they should, increasing the risk of electrical fires. This failure is often attributed to the design and materials used in the breakers, which can cause the internal mechanisms to become stuck or fail to operate properly under fault conditions. The Consumer Product Safety Commission investigated FPE breakers in the past but never issued a formal recall, despite evidence of potential safety hazards. This lack of official action has led to ongoing debate and concern within the electrical industry and among homeowners. Although no longer manufactured, FPE breakers can still be found in many older homes and buildings. Their age and the potential for degradation over time further increase the risk of failure. Due to the safety concerns associated with FB breakers, the standard recommendation is to replace them. A complete replacement of the FB breaker panel with a modern circuit breaker panel is the most effective way to mitigate the risk. This ensures that all breakers in the system are reliable and meet current safety standards. When replacing an FP panel, it is essential to hire a qualified and licensed electrician. They can assess the existing electrical system, ensure proper installation of the new panel, and verify that all circuits are functioning correctly. Replacement breakers should meet or exceed the original panel specifications in terms of amperage and voltage ratings. The new panel should also include features such as arc fault circuit interrupters and ground fault circuit interrupters for enhanced safety. Even if an FB breaker appears to be functioning normally, it is still recommended to replace it. The risk of future failure remains, and a proactive replacement ensures a safer electrical system. Regular electrical inspections are crucial for identifying potential hazards, including the presence of FB breakers. A qualified electrician can perform a thorough inspection and recommend appropriate actions. Replacing FB breakers is a worthwhile investment in home safety. The cost of replacement is typically far less than the potential damage and risk associated with an electrical fire. It is also a good idea to inform potential home buyers about the presence of FB breakers and the recommendation for replacement. This transparency can help ensure that the new owners are aware of the potential safety issue and can take appropriate action. If the budget is a concern, explore options for phased replacement, prioritizing circuits with high loads or known issues. Consult with a licensed electrician to determine the most cost-effective and safest approach. Replacing Federal Pacific electric breakers is a prudent step to enhance electrical safety and reduce the risk of fires. The cost of replacing Federal Pacific breakers can vary depending on several factors, including the size of the electrical panel, the number of breakers that need to be replaced, and the electrician's labor rates. Here's a breakdown of the potential costs involved in replacing Federal Pacific breakers. The cost of a new circuit breaker panel can range from $500 to $2,000 or more, depending on the brand, size, and features. A larger panel with more circuit slots and higher amperage ratings will typically cost more. Individual circuit breakers typically range from $10 to $50 each, depending on the amperage rating and type. For example, arc fault circuit interrupter and ground fault circuit interrupter breakers are more expensive than standard circuit breakers. Labor costs can vary depending on the electrician's hourly rate and the complexity of the job. A simple breaker replacement may cost a few $100s, while a complete panel replacement can cost several hundred to over $1,000 in labor. Permits are often required for electrical work, including panel replacements. Permit fees can vary depending on the location and the scope of the project, but they typically range from $50 to $200. There may be additional costs if the existing wiring needs to be upgraded or if there are any unexpected issues during the replacement process. For example, if the wiring is old or damaged, it may need to be replaced to ensure the safety and reliability of the electrical system. To get an accurate estimate of the cost of replacing Federal Pacific breakers, it's best to obtain quotes from several qualified and licensed electricians. They can assess the specific situation and provide a detailed estimate that includes the cost of the new panel, breakers, labor, and permits. When comparing quotes, be sure to ask about the electrician's experience with Federal Pacific breaker replacements and their knowledge of local electrical codes and regulations. Replacing Federal Pacific breakers is an investment in home safety, and it's important to choose a qualified electrician and use high-quality materials to ensure the job is done correctly. Remember that Federal Pacific breakers have a history of failure and pose a safety hazard, so replacing them is a proactive step to protect your home and family. The National Electrical Code, or NEC, doesn't specifically prohibit the installation of Federal Pacific Electric, or FPE breakers. However, due to their documented history of failure and potential safety hazards, it is strongly recommended to replace them rather than install new ones. Here's a more detailed explanation of the NEC stance on FPE breakers and why replacement is the best course of action. The NEC doesn't explicitly list specific brands or manufacturers of breakers that are prohibited. Instead, the NEC focuses on performance and safety standards that all electrical equipment must meet. The NEC requires that all electrical equipment be listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories, or This listing indicates that the equipment has been tested and found to meet certain safety standards. While FP breakers were originally listed by UL, the subsequent performance issues and high failure rates have raised concerns about their continued compliance with these standards. The NEC requires that circuit breakers be properly sized for the circuits they protect. This means that the breaker's amperage rating must match the ampacity of the conductors in the circuit. If a breaker is undersized, it may trip unnecessarily. If it is oversized, it may not trip during an overcurrent or short circuit, which can lead to overheating and fires. The NEC requires that circuit breakers be readily accessible and properly maintained. This means that they should be easy to reach and operate, and they should be inspected regularly to ensure that they are functioning properly. If a breaker is found to be defective or damaged, it should be replaced immediately. Although the NEC doesn't specifically prohibit the installation of FE breakers, it does contain general requirements for safety and performance that may be difficult to meet with these breakers due to their known issues. The NEC emphasizes the importance of using listed and labeled equipment, ensuring proper sizing and installation, and maintaining electrical systems in good working order. Given the documented history of failure and potential safety hazards associated with FB breakers, it is generally not advisable to install new ones, even if they are still available for purchase. Replacing existing FB breakers with modern, reliable breakers is the safest and most prudent course of action. Modern circuit breakers offer improved performance, reliability, and safety features compared to older FPE breakers. They are designed to trip quickly and reliably under overcurrent and short circuit conditions, providing better protection for electrical systems and occupants. Replacing FE breakers is an investment in home safety and can help prevent electrical fires and other hazards. It's important to consult with a qualified and licensed electrician to assess the electrical system and determine the best course of action. They can provide recommendations for replacement breakers and ensure that the installation is done safely and correctly. The National Electrical Code provides a comprehensive set of guidelines for ensuring the safety of electrical installations. While it doesn't specifically ban FE breakers, the underlying principles of safety and reliability strongly suggest that they should be replaced due to their known issues.